What if I told you that we might actually have the tools to reverse climate change? For decades, we've been told that global warming is an unstoppable crisis, that rising temperatures, melting ice caps, and extreme weather events are beyond our control. But what if that's not entirely true? What if science, technology, and nature itself hold the key to undoing the damage? This question isn't just theoretical. It's a challenge that scientists, policymakers, and innovators around the world are racing to answer. Why this matters more than ever. But climate change isn't a distant problem. It's happening right now. Every year, we see record-breaking heatwaves, devastating wildfires, intensifying hurricanes, and rising sea levels swallowing coastlines. Cities are becoming unlivable, food production is being disrupted, and millions of people are being displaced by climate-related disasters. The urgency to act has never been greater. But with urgency comes another pressing concern. Have we already reached the point of no return? The biggest misconceptions about climate change. One of the biggest misconceptions about climate change is that it's irreversible. Many people believe that we are past the tipping point, that no matter what we do, the damage is already locked in. This assumption is partly fueled by alarming headlines and doomsday predictions. However, the reality is more complex. Some aspects of climate change are indeed difficult to reverse, but others can still be mitigated, slowed down, or even undone. The question isn't whether reversal is possible, it's how, when, and at what scale. Another common misconception is that individual actions don't matter. While systemic change is crucial, history has shown that technological advancements, policy shifts, and collective efforts can make a measurable difference. The story of climate change isn't just about destruction, it's also about resilience, adaptation, and the potential for transformation. How we got here. A brief history of climate change science. To understand whether climate change can be reversed, we need to look at how we got here in the first place. The Industrial Revolution in the 18th century marked a turning point for humanity, bringing advancements in energy, manufacturing, and transportation. But it also triggered an explosion in carbon emissions, as coal, oil, and natural gas became the backbone of modern civilization. For decades, scientists have been tracking the impact of fossil fuel consumption. In the late 19th century, researchers like Svante Arrhenius first proposed the connection between carbon dioxide and global temperatures. By the 20th century, climate models confirmed that human activities were warming the planet at an unprecedented rate. The evidence has only grown stronger, with satellite data, ice core samples, and ocean measurements all pointing to the same conclusion: climate change is real, and it's accelerating. What this video will cover: the debate over reversing climate change is filled with scientific breakthroughs, technological innovations, and controversial ideas. This video will explore the science behind reversing climate change, the latest solutions being developed, and the most promising strategies that could shape the future. From carbon capture and geoengineering to nature-based solutions and political challenges, we'll break down what's possible, what's still a theory, and what needs to happen for real change to occur. By the end, you'll have a deeper understanding of the fight against climate change and whether we still have time to turn things around. The science of climate change. How climate change works. Climate change is not just about warmer summers or unpredictable weather, it's a fundamental shift in the Earth's climate system. At its core, the driving force behind climate change is the greenhouse effect. Certain gases in the atmosphere, such as carbon dioxide, methane, and nitrous oxide, trap heat from the sun, preventing it from escaping back into space. This process is natural and essential for life on Earth, maintaining temperatures within a habitable range. However, human activity has drastically increased greenhouse gas concentrations, amplifying this effect and leading to global warming. The carbon cycle plays a crucial role in regulating Earth's climate. Normally, carbon dioxide is absorbed by plants during photosynthesis, stored in forests and oceans, and released back into the atmosphere through respiration, volcanic activity, and the decay of organic matter. But industrial activities, deforestation, and large-scale burning of fossil fuels have disrupted this balance, leading to excessive carbon buildup in the atmosphere. The more carbon we release, the more heat gets trapped, causing a cascade of environmental changes. Feedback loops make this problem even more complex. One major example is the Arctic ice albedo effect. Ice and snow reflect sunlight, helping to keep the planet cool. As temperatures rise, ice melts, exposing darker ocean water that absorbs more heat, leading to even more melting. Another feedback loop involves permafrost, frozen ground that stores vast amounts of carbon. As it thaws due to rising temperatures, it releases methane, a greenhouse gas far more potent than carbon dioxide, accelerating warming even further. These loops create self-reinforcing cycles that make climate change not just a gradual process but a rapidly intensifying crisis. The evidence of climate change. The proof of climate change is overwhelming. Global temperatures have risen by more than 1.1 degrees Celsius since pre-industrial times, with the past decade being the hottest on record. This warming trend is not random. It follows the trajectory of increasing greenhouse gas emissions. Climate models, which have accurately predicted temperature changes for decades, confirm that human activities are the primary driver. Ice caps and glaciers, once considered permanent fixtures of the planet, are melting at an alarming rate. Greenland and Antarctica are losing ice at a pace that threatens to raise global sea levels by several meters in the coming centuries. In some regions, entire glaciers have disappeared, disrupting ecosystems and water supplies that depend on glacial runoff. The Arctic, in particular, is warming nearly 4 times faster than the rest of the planet, leading to shrinking sea ice that disrupts marine life and contributes to extreme weather patterns worldwide. Ocean acidification is another major consequence of increased carbon dioxide emissions. The world's oceans absorb roughly 30% of the carbon dioxide released into the atmosphere. While this helps slow atmospheric warming, it comes at a cost, changing the chemistry of seawater. The increased acidity dissolves calcium carbonate, a crucial component of coral reefs, shellfish, and marine organisms. As a result, coral reefs are dying at unprecedented rates, endangering biodiversity and marine food chains. Acidification also affects fish populations, reducing their ability to reproduce and survive, which could lead to severe disruptions in global fisheries and food supplies. Tipping points. Are we approaching the point of no return? Scientists warn that the Earth's climate has certain tipping points, thresholds beyond which damage becomes irreversible. One of the most concerning is the collapse of the Atlantic Meridional Overturning Circulation, AMOC, a major ocean current that regulates global climate patterns. If this system weakens or shuts down due to melting ice disrupting its flow, it could trigger catastrophic shifts in weather, making Europe significantly colder, increasing droughts in Africa, and intensifying hurricanes in the Americas. The Amazon rainforest, often called the lungs of the Earth, is another tipping point. It absorbs vast amounts of carbon dioxide, helping to regulate global temperatures. However, deforestation combined with climate change is pushing it toward a dangerous transition where it could shift from a carbon sink to a carbon source. If too much of the rainforest is lost, it could enter a feedback loop where rising temperatures lead to more forest loss, releasing even more carbon into the atmosphere. Methane release from permafrost is also a major concern. Vast amounts of methane are trapped in Arctic permafrost and ocean sediments. As temperatures rise, this methane is released into the atmosphere, further accelerating global warming. Unlike carbon dioxide, which can remain in the atmosphere for centuries, methane is far more potent in the short term, making it a critical factor in near-term climate impacts. The big question remains: have we already passed these tipping points? Some scientists argue that while we are dangerously close, there is still time to act if we drastically reduce emissions and deploy large-scale carbon removal strategies. Others warn that certain feedback loops may have already been triggered, meaning some level of climate disruption is now unavoidable. Is climate change self-regulating? A controversial debate. There is a controversial argument among some scientists that climate change could be partially self-regulating. The idea is that as the Earth warms, natural processes may kick in to slow down or even counteract some of the damage. One example often cited is the increase in plant growth due to higher carbon dioxide levels, leading to more carbon sequestration. In theory, forests and algae blooms in the ocean could absorb excess carbon and stabilize temperatures. However, this concept is highly debated because it assumes ecosystems can adapt fast enough to keep up with human emissions, which so far has not been the case. Another argument suggests that volcanic activity and natural weathering processes could help pull carbon dioxide from the atmosphere over thousands of years. While technically true, these processes work on geological timescales, meaning they're not fast enough to counteract human-caused climate change in the immediate future. Geoengineering is another controversial idea that falls into the discussion of climate self-regulation. Some scientists propose artificially altering the climate by injecting aerosols into the stratosphere to reflect sunlight or fertilizing the ocean to stimulate plankton growth, which absorbs carbon. While these ideas sound promising, they come with serious risks, including potential unintended consequences such as disrupting weather patterns or causing regional droughts. Ultimately, while some aspects of climate change may have natural balancing mechanisms, relying on self-regulation is risky and uncertain. The overwhelming scientific consensus remains that human intervention is necessary to mitigate and reverse the worst effects. The longer we wait, the harder it becomes to control the outcome, making it critical to act before we push past more irreversible tipping points. The science of climate change is complex, but the evidence is clear. The planet is warming due to human activity, and the consequences are accelerating. While some argue that the Earth has natural mechanisms to regulate its climate, relying on this theory is a gamble we cannot afford to take. The next step is understanding whether reversing climate change is even possible and what solutions scientists are exploring to tackle the crisis before it's too late. Is reversing climate change even possible? What does reversing climate change really mean? When people talk about reversing climate change, the first question that arises is what that actually means. Does it mean stopping further warming, or does it mean undoing the damage that has already been done? There is a crucial difference between mitigation, reducing future emissions, and reversal, which would involve removing excess carbon from the atmosphere and restoring the climate to a pre-industrial state. Stopping climate change at its current level would still require drastic reductions in greenhouse gas emissions, transitioning away from fossil fuels, and widespread adoption of clean energy. But that alone wouldn't undo the decades of accumulated carbon dioxide in the atmosphere. To truly reverse climate change, we would need to not only halt emissions but actively remove carbon from the air on an unprecedented scale. This is an enormous challenge, as it requires technologies and natural solutions that are still in their infancy. Some believe that a combination of carbon removal, geoengineering, and large-scale reforestation could bring temperatures back down over time. Others argue that even with extreme efforts, the damage to ecosystems, ocean acidification, and ice sheet loss may be irreversible. The reality is likely somewhere in between. Some aspects of climate change may be reversed, while others could take centuries or even millennia to restore. Scientific perspectives on climate reversal leading climate scientists remain divided on whether full climate reversal is possible. Many agree that reducing emissions is non-negotiable, but there is debate about whether carbon removal techniques can ever be scaled up enough to counteract centuries of industrial pollution. James Hansen, one of the earliest scientists to warn about global warming, argues that while reducing emissions is essential, carbon removal must be part of the equation if we ever hope to return to pre-industrial temperature levels. He points to historical carbon dioxide fluctuations as evidence that the planet can recover, but emphasizes that the timeline for natural recovery is far too slow to prevent severe damage. Michael Mann, another prominent climate scientist, is more skeptical of full reversal. He warns against the idea that carbon removal technologies alone can save us, calling it a dangerous distraction from the urgent need to cut emissions. He argues that while some carbon capture methods show promise, they remain expensive, energy-intensive, and difficult to scale. He also warns of unintended consequences, such as the potential for geoengineering projects to disrupt weather patterns or create unforeseen environmental risks. Despite these challenges, some researchers remain optimistic. Scientists working on direct air capture technology believe that with enough investment, machines could one day pull significant amounts of CO from the air and store it underground. Others believe that regenerative agriculture and reforestation could make a meaningful difference in sequestering carbon naturally. The challenge is implementing these solutions at a scale large enough to reverse decades of emissions. Lessons from Earth's climate history. The Earth has gone through dramatic climate shifts before, including ice ages and periods of extreme warmth. These natural fluctuations happened over thousands or even millions of years, driven by factors such as volcanic activity, changes in Earth's orbit, and natural carbon cycles. One of the most significant historical climate events was the Paleocene-Eocene thermal maximum, PETM, around 56 million years ago, when massive amounts of carbon were released into the atmosphere, raising global temperatures by up to 8 degrees Celsius. Over tens of thousands of years, the planet gradually cooled as natural processes removed excess carbon from the air through weathering, ocean absorption, and the burial of organic matter. This suggests that Earth has mechanisms for regulating its climate, but the timescales involved are far too long for human civilization to rely on natural recovery. Another example is the cooling period following the eruption of Mount Tambora in 1815, which released large amounts of sulfur dioxide into the atmosphere, temporarily lowering global temperatures. This highlights the potential of geoengineering techniques, such as stratospheric aerosol injection, to artificially cool the planet. However, these methods do not address the root cause of climate change, excess greenhouse gases, and could have unintended side effects. The key lesson from Earth's climate history is that while natural processes can eventually restore balance, they operate on geological timeframes that are incompatible with the urgency of today's crisis. This means that if we want to reverse climate change within a time frame that prevents catastrophic consequences, human intervention will be required. The biggest challenge: carbon buildup and why it's so hard to remove. The most significant obstacle to reversing climate change is the sheer volume of carbon dioxide already in the atmosphere. Since the Industrial Revolution, humans have released over 1.5 trillion metric tons of CO, with more than 400 billion metric tons added in just the past 30 years. Unlike pollutants that can break down quickly, carbon dioxide can linger in the atmosphere for centuries, making it incredibly difficult to remove once it's there. One of the biggest problems is that most natural carbon sinks, such as forests and oceans, are already under stress. Deforestation has reduced the planet's ability to absorb CO, while oceans are becoming saturated with carbon, leading to acidification that threatens marine life. Planting trees can help, but it would require trillions of trees to offset current emissions, and even then, forests take decades to mature. Technological solutions, such as direct air capture, DAC, involve machines that pull carbon dioxide from the air and store it underground or convert it into materials like synthetic fuels. While promising, these systems are currently expensive, requiring massive energy inputs to function. A single DAC plant today removes only about 4,000 tons of CO per year, while global emissions exceed 40 billion tons annually. This means that even if thousands of these plants were built, they would still struggle to make a significant dent in atmospheric carbon levels. Other proposed solutions include enhanced weathering, which accelerates the natural process of rock formations absorbing CO, and biochar, a method of trapping carbon in soil. While these techniques have potential, they are not yet deployed at a scale that can significantly reverse climate change. The challenge is not just removing carbon, but doing so fast enough to counteract ongoing emissions. Even if all fossil fuel use stopped today, the planet would continue warming due to the carbon already in the atmosphere. Scientists estimate that to meaningfully reverse climate change, we would need to remove 10 billion tons of CO per year by 2050, a scale that far exceeds our current capabilities. Despite these challenges, some experts believe that a combination of aggressive emission reductions, large-scale carbon removal, and potential geoengineering interventions could still tip the balance in our favor. Whether this will be enough, and whether the world will act quickly enough, is still uncertain. The reality is that reversing climate change is not impossible, but it is a monumental challenge that requires coordinated global effort. The next step is to explore the role of technology in this fight, including both the promising solutions and the potential risks that come with them. The role of technology in climate reversal, carbon capture and storage, how it works, successes, and failures. One of the most widely discussed technological solutions for reversing climate change is carbon capture and storage, or CCS. The concept is simple: capture carbon dioxide emissions at the source before they enter the atmosphere and store them underground in geological formations where they cannot contribute to global warming. This technology has been implemented in industries like power plants, steel production, and cement manufacturing, which are some of the biggest sources of emissions. CCS works by separating carbon dioxide from other gases produced during industrial processes, compressing it into a liquid form, and injecting it deep underground into depleted oil fields or saline aquifers. In theory, this prevents carbon dioxide from accumulating in the atmosphere and contributing to the greenhouse effect. Some projects have shown promise, such as the Sleipner gas field in Norway, which has been successfully storing carbon dioxide beneath the North Sea for over 2 decades. The Boundary Dam Power Station in Canada has also demonstrated that CCS can significantly reduce emissions from coal-fired plants. Despite these successes, CCS has faced major challenges. The biggest issue is cost. Capturing and storing carbon is expensive, with estimates ranging from $50 to $100 per ton of CO removed. This makes it economically unfeasible for widespread adoption without government subsidies or carbon pricing mechanisms. Another problem is that CCS does not eliminate emissions entirely, it only reduces them at the source. Many critics argue that instead of investing in expensive CCS technology to prolong the life of fossil fuels, resources should be directed toward renewable energy, which eliminates emissions altogether. Some CCS projects have also failed, such as the Kemper coal plant in Mississippi, which was supposed to be a model for clean coal technology but collapsed due to technical and financial difficulties. This raises the question of whether CCS can ever be a large-scale solution or if it is simply an excuse for industries to delay transitioning away from fossil fuels. Direct air capture. Can we vacuum carbon dioxide from the sky? If carbon capture at the source is not enough, why not remove carbon dioxide directly from the air? That is the idea behind direct air capture, or DAC, a technology that aims to vacuum carbon dioxide from the atmosphere, regardless of its origin. DAC involves using giant fans to pull in air, passing it through chemical filters that absorb CO, and then either storing it underground or using it to make synthetic fuels, plastics, or even carbon-negative building materials. Companies like Climeworks in Switzerland and Carbon Engineering in Canada are leading the way in DAC development. Climeworks has built facilities that remove small amounts of CO from the air and inject it into basalt rock formations, where it mineralizes and becomes permanently stored. Carbon Engineering is working on scaling up its technology to produce carbon-neutral fuels by capturing atmospheric carbon dioxide and combining it with hydrogen. The main challenge with DAC is the amount of energy required to run these machines. Current DAC systems consume large amounts of electricity, which raises concerns about whether the process is truly sustainable unless powered by renewable energy. The cost is also a major barrier, with DAC currently priced at $250 to $600 per ton of CO removed, far too expensive for large-scale deployment. To have a meaningful impact on climate change, DAC would need to remove billions of tons of CO per year, requiring vast amounts of land, infrastructure, and energy. Despite these obstacles, DAC remains one of the most promising carbon removal technologies because it does not rely on emissions reductions alone. It actively removes carbon dioxide already in the atmosphere. If costs can be lowered through technological advancements and policy incentives, DAC could play a significant role in climate reversal. Geoengineering solutions, reflecting sunlight, artificial clouds, and ocean fertilization. If reducing emissions and removing carbon prove too slow, could we use technology to artificially cool the planet? Geoengineering, or climate engineering, involves large-scale interventions to manipulate Earth's climate and counteract global warming. One of the most widely studied methods is solar radiation management, which involves reflecting sunlight away from the Earth to reduce temperatures. One approach is stratospheric aerosol injection, where tiny sulfur particles are sprayed into the upper atmosphere to mimic the cooling effect of volcanic eruptions. When Mount Pinatubo erupted in 1991, it released massive amounts of sulfur dioxide, temporarily lowering global temperatures by about 0.5 degrees Celsius for over a year. Scientists believe a similar technique could be used to artificially cool the planet, buying time for other climate solutions to take effect. Another idea is marine cloud brightening, where salt particles are sprayed into clouds to make them more reflective, increasing their ability to bounce sunlight back into space. This technique has been proposed as a way to cool specific regions, such as the Arctic, where melting ice is accelerating warming. A different form of geoengineering focuses on the oceans. Iron fertilization is the concept of adding iron particles to the ocean to stimulate the growth of phytoplankton, which absorb carbon dioxide through photosynthesis. Theoretically, when these plankton die, they sink to the ocean floor, trapping carbon in deep-sea sediments. Experiments have shown that iron fertilization can increase plankton growth, but its long-term effectiveness and environmental risks remain uncertain. While geoengineering presents potential solutions, it also raises ethical, political, and environmental concerns. Are these solutions actually dangerous? Potential unintended consequences. The idea of manipulating the climate on a global scale is controversial. While geoengineering could provide a temporary cooling effect, it does not address the root cause of climate change, greenhouse gas emissions. There is also the risk of unintended consequences. Stratospheric aerosol injection, for example, could disrupt rainfall patterns, potentially causing droughts in some regions while cooling others. Another major concern is what happens if geoengineering is suddenly stopped. If sulfate aerosols were injected into the stratosphere for decades and then suddenly halted, the Earth could experience a rapid surge in warming, known as the termination shock. This could lead to extreme climate disruptions, making conditions worse than before the intervention. There are also geopolitical risks. Who gets to decide how and when to deploy geoengineering? If one country unilaterally decides to conduct large-scale climate modification, it could trigger conflicts with other nations that might suffer unintended consequences. Some scientists warn that geoengineering could become a dangerous tool, with the potential for weather manipulation to be weaponized. Carbon capture, direct air capture, and geoengineering all offer potential pathways to slowing or reversing climate change, but each comes with challenges and risks. None of these solutions alone will be enough to restore the climate to pre-industrial conditions. The real question is whether these technologies can be scaled up fast enough to make a meaningful impact before the effects of climate change become irreversible. The next step is to explore nature's own solutions and whether forests, oceans, and ecosystems can play a role in reversing climate change without the risks associated with human-engineered interventions. Nature's solutions to climate change: reforestation and afforestation. How many trees do we actually need? Forests are one of the most effective natural tools for fighting climate change. Trees absorb carbon dioxide from the atmosphere through photosynthesis, storing it in their trunks, branches, and roots. Reforestation, which involves restoring forests that have been cut down, and afforestation, which means planting trees in areas that were not previously forested, are often promoted as essential climate solutions. The scale of deforestation in recent decades has been staggering. The Amazon rainforest alone has lost over 17% of its forest cover in the past 50 years, while tropical forests worldwide continue to be cleared for agriculture, logging, and urban development. Scientists estimate that global forests absorb around 7.6 billion metric tons of CO per year, but that is not enough to offset the 40 billion metric tons emitted annually by human activities. Restoring lost forests could make a significant difference, but how many trees would be needed to reverse climate change? A landmark study published in Science estimated that planting 1 trillion trees could remove up to 200 billion metric tons of CO over several decades. This is equivalent to nearly 5 years' worth of human emissions at current levels. While this sounds promising, planting trees alone is not a silver bullet. Forests take time to mature, and carbon sequestration is a slow process. Additionally, large-scale tree planting requires vast amounts of land, potentially competing with agricultural and urban needs. Reforestation projects have had mixed results. Some efforts, such as China's Great Green Wall, have successfully restored millions of acres of degraded land, while others have failed due to poor planning and unsuitable tree species. Monoculture plantations, where a single tree species is planted, can actually harm biodiversity and reduce resilience to pests and disease. The key to successful reforestation lies in restoring diverse, native ecosystems rather than simply covering landscapes with fast-growing trees. Regenerative agriculture. How farming can trap carbon and restore ecosystems. Agriculture is one of the largest sources of greenhouse gas emissions, contributing nearly 25% of global CO, methane, and nitrous oxide emissions. Industrial farming relies heavily on synthetic fertilizers, monoculture crops, and intensive tilling, all of which degrade soil health and release stored carbon into the atmosphere. Regenerative agriculture offers a different approach, one that not only produces food but also helps trap carbon and restore ecosystems. Healthy soils are one of the planet's largest carbon sinks, capable of holding 3 times more carbon than the atmosphere. Practices such as no-till farming, cover cropping, and rotational grazing help build organic matter in soil, allowing it to absorb and retain more carbon. By improving soil structure, these techniques also reduce erosion, increase water retention, and enhance biodiversity. Another key strategy is agroforestry, which integrates trees and shrubs into farmland. By combining crops with tree cover, agroforestry mimics natural ecosystems, improving soil fertility while sequestering carbon. Studies have shown that well-managed agroforestry systems can store 5 to 10 times more carbon per hectare than conventional farms. The potential for regenerative agriculture to combat climate change is significant. If adopted globally, regenerative farming could sequester up to 23 gigatons of CO by 2050. However, there are challenges to widespread adoption. Many farmers face economic pressures that make it difficult to transition away from conventional methods, and there is still a lack of incentives for sustainable farming practices. Scaling up regenerative agriculture requires policy changes, financial support, and shifts in consumer demand toward food grown in climate-friendly ways. Ocean-based solutions, kelp forests, marine permaculture, and deep-sea carbon storage. The ocean is the world's largest carbon sink, absorbing around 30% of human carbon dioxide emissions and regulating global climate patterns. However, as the ocean takes in more carbon, it becomes more acidic, endangering marine life and weakening its ability to store carbon in the future. To enhance the ocean's role in climate mitigation, scientists are exploring nature-based solutions that go beyond just preserving marine ecosystems. Kelp forests, often referred to as the rainforests of the sea, grow rapidly and absorb large amounts of CO. Unlike trees, which take decades to mature, kelp can grow up to 2 feet per day, making it one of the fastest carbon sequestering organisms on the planet. By expanding kelp farming and marine permaculture, it may be possible to scale up ocean-based carbon capture. Kelp farms can also provide sustainable food sources, biofuels, and materials for biodegradable plastics, creating economic incentives for marine conservation. Deep-sea carbon storage is another area of research. When marine plants like kelp die, they naturally sink to the ocean floor, where their carbon is locked away for centuries. Some scientists are investigating ways to accelerate this process by strategically placing seaweed farms in locations where biomass is more likely to sink permanently. This approach could enhance the ocean's ability to store carbon without disrupting delicate marine ecosystems. Another emerging concept is ocean alkalinity enhancement, which involves adding minerals like olivine to seawater to increase its ability to absorb CO. The theory is that by chemically altering ocean water, it could help remove billions of tons of carbon from the atmosphere while also counteracting acidification. While promising in theory, large-scale deployment of this method remains untested, and scientists are still studying potential ecological risks. Can nature alone reverse climate change? The limits of natural solutions. Nature offers some of the most powerful tools for combating climate change, but can it truly reverse the damage on its own? While forests, soil, and oceans play a critical role in absorbing and storing carbon, they cannot keep pace with current emissions without additional human intervention. The scale of the problem is simply too vast. One of the biggest limitations is time. Trees and soil take years to sequester significant amounts of carbon, while ocean-based solutions are still in their experimental stages. Given the rapid pace of global warming, waiting for natural systems to catch up is not a viable strategy. There is also the risk of climate-driven feedback loops, where rising temperatures weaken nature's ability to regulate carbon. Droughts, wildfires, and deforestation reduce the effectiveness of forests, while ocean warming disrupts marine carbon cycles. Another challenge is land availability. Large-scale reforestation and regenerative agriculture require vast amounts of space, which could conflict with food production and urban expansion. Finding a balance between conservation and human development is a complex issue that requires careful planning and policy support. While nature-based solutions are essential, they must be combined with technological innovations and systemic policy changes to achieve meaningful climate reversal. The best approach is an integrated strategy that combines carbon capture, renewable energy, reforestation, and regenerative farming. Without immediate action on multiple fronts, nature alone will not be able to undo the damage that has already been done. The next step in understanding climate reversal is examining the political and economic barriers that stand in the way of large-scale action. Even with powerful solutions available, the reality is that financial interests, government policies, and global power dynamics play a major role in determining how fast or slow we move toward meaningful change. The industries that profit from inaction. While climate change is a global crisis threatening ecosystems, economies, and human health, there are industries that benefit from inaction. Fossil fuel companies, which generate trillions of dollars annually, have a vested interest in maintaining the status quo. Oil, coal, and natural gas producers continue to extract and sell resources that are directly responsible for greenhouse gas emissions. These industries invest heavily in lobbying efforts to delay or weaken climate policies, ensuring their profitability remains intact. Beyond the fossil fuel sector, other industries profit from climate instability. The insurance industry, for example, has adjusted to the growing frequency of natural disasters by raising premiums and limiting coverage in high-risk areas. Agricultural companies have expanded their operations into new territories as traditional farmlands become less viable due to shifting climate patterns. Even private water companies see financial opportunities in worsening drought conditions, as scarcity increases demand for privatized water supplies. Large-scale construction firms also benefit from rebuilding efforts after hurricanes, wildfires, and flooding. Instead of preventing disasters, some companies see financial gain in disaster response. Meanwhile, the mining industry is accelerating operations for lithium, cobalt, and rare earth metals, which are critical for electric vehicle batteries and renewable energy technology. While these materials are necessary for a low-carbon future, their extraction often comes with severe environmental costs. As long as there are industries profiting from inaction, there will be resistance to meaningful climate solutions. Governments worldwide face pressure from these corporations, making it difficult to implement aggressive climate policies. The conflict between economic interests and environmental sustainability remains one of the biggest obstacles to reversing climate change. Carbon taxes versus carbon credits, are they effective or just a loophole? Carbon pricing is often presented as a market-driven solution to climate change, with two main approaches: carbon taxes and carbon credits. A carbon tax places a direct cost on carbon emissions, incentivizing companies to reduce pollution by making fossil fuel consumption more expensive. In contrast, carbon credits allow companies to offset their emissions by purchasing credits from carbon reduction projects, such as reforestation or renewable energy initiatives. Theoretically, both methods encourage emissions reductions, but in practice, they have significant weaknesses. Carbon taxes are often politically unpopular because they can raise energy prices for consumers. Industries that rely on fossil fuels argue that carbon taxes hurt economic growth and push jobs overseas to countries with weaker regulations. Many governments hesitate to enforce strict carbon pricing out of fear that it could damage their economies. Carbon credits, on the other hand, have been criticized as a loophole that allows corporations to continue polluting while appearing environmentally responsible. Many companies buy carbon offsets without actually reducing their own emissions. Some carbon credit programs lack transparency, and studies have found that certain offset projects, such as tree planting initiatives, fail to deliver the promised reductions. There have also been cases of companies double counting carbon credits, effectively inflating their climate commitments without meaningful action. The effectiveness of carbon pricing depends on strict enforcement and accountability. Countries with well-regulated carbon tax systems, such as Sweden and Canada, have seen measurable emissions reductions. However, global implementation remains inconsistent. Without international coordination, companies can simply relocate operations to countries with weaker regulations, undermining the overall impact. While carbon pricing can be a useful tool, it is not a standalone solution. It must be accompanied by stricter emissions regulations, investment in clean energy, and policies that prevent industries from exploiting loopholes. Fossil fuel phase-out challenges. Why it's not as simple as just stopping oil production. Phasing out fossil fuels is one of the most critical steps in reversing climate change, yet it remains one of the most difficult to achieve. The global economy is still heavily dependent on oil, coal, and natural gas, with fossil fuels providing over 80% of the world's energy supply. Despite rapid advancements in renewable energy, many industries, including transportation, manufacturing, and heavy industry, still lack viable alternatives. One of the biggest challenges is infrastructure. Many countries have built their economies around fossil fuels, with pipelines, refineries, and power plants designed for long-term use. Shifting away from these systems requires massive investments in new energy infrastructure, which takes time and resources. Developing nations, in particular, face difficulties transitioning to renewables due to financial constraints and energy security concerns. Political resistance also plays a major role. Fossil fuel companies exert enormous influence on policymakers through lobbying and campaign donations. In countries where oil and gas are major economic drivers, such as the United States, Russia, and Saudi Arabia, political leaders often prioritize short-term economic growth over long-term climate goals. Some governments continue to subsidize fossil fuel production, making it even harder for renewable energy to compete. Job loss is another significant barrier. The fossil fuel industry employs millions of workers worldwide, and a rapid transition away from coal, oil, and gas would leave many without employment. A just transition requires large-scale workforce retraining programs, investment in green jobs, and policies that ensure affected communities are not left behind. Without these measures, resistance from workers and unions could slow down climate action. Despite these challenges, some countries have made progress. Denmark has committed to ending new oil exploration in the North Sea by 2050, and Costa Rica has already transitioned to nearly 100% renewable energy. The shift away from fossil fuels is possible, but it requires strong political will, economic planning, geopolitical conflicts over climate action, how countries are divided on solutions. Climate change is a global issue, but solutions are often hindered by geopolitical conflicts. Different countries have different economic priorities, political interests and levels of responsibility for historical emissions. Developed nations, such as the United States and those in the European Union, have contributed the most to historical carbon emissions, while developing countries argue that they should not be forced to curb economic growth to fix a problem they did not create. One of the biggest conflicts in global climate negotiations is the issue of climate finance. Wealthy nations have pledged to provide financial support to developing countries to help them transition to clean energy and adapt to climate impacts. However, many of these commitments remain unmet. The $100 billion per year climate finance goal set by developed nations has consistently fallen short, leading to frustration among developing countries that struggle to access funding for climate adaptation and mitigation projects. There are also tensions over emissions reduction targets. Some countries, like China and India, argue that their priority is economic development and poverty reduction, and that wealthier nations should bear the primary responsibility for cutting emissions. The reliance on coal in countries like India makes rapid decarbonization difficult without significant financial and technological support. Meanwhile, oil-producing countries such as Saudi Arabia and Russia actively resist aggressive climate policies that threaten their economic interests. International climate agreements, such as the Paris Agreement, have attempted to create a framework for global cooperation, but enforcement remains a challenge. There is no binding mechanism to force countries to meet their emissions targets, leading to uneven progress. Some nations have made ambitious commitments, while others continue expanding fossil fuel production. Political instability, economic crises, and shifting government priorities further complicate the global response to climate change. Despite these conflicts, there are areas of collaboration. The rapid development of renewable energy technology, international carbon markets, and joint climate research efforts demonstrate that cooperation is possible. However, until major geopolitical tensions are addressed, meaningful global action will remain fragmented. Reversing climate change requires more than just technology and scientific advancements. The political and economic landscape plays a crucial role in determining how fast or slow progress is made. Industries that profit from inaction, weak climate policies, and geopolitical divisions continue to hinder large-scale solutions. Without addressing these barriers, even the best climate strategies will struggle to be implemented. The next step is understanding the role of individuals and collective action. Can personal choices truly make a difference, or is systemic change the only way forward? Do individual actions matter? The debate on personal responsibility versus corporate impact. One of the biggest debates in the fight against climate change is whether individual actions truly make a difference or if real change can only come from governments and corporations. Many people are told that they should reduce their carbon footprint by driving less, eating less meat, and consuming less energy. While these choices are important, critics argue that placing the burden on individuals distracts from the much larger issue: corporate pollution and government inaction. The data supports this argument. Just 100 companies are responsible for over 70% of global emissions. These companies, primarily fossil fuel producers, continue extracting and burning resources while shifting responsibility onto consumers. Meanwhile, government subsidies for oil, coal, and gas industries amount to $7 trillion globally each year, making it clear that systemic change, not just personal lifestyle adjustments, is needed to reverse climate change. However, dismissing individual actions entirely ignores the role that consumer behavior plays in driving market demand. If millions of people choose electric vehicles over gas-powered cars, the auto industry will be forced to adapt. If plant-based diets gain popularity, food companies will invest more in sustainable alternatives. Consumer choices have already reshaped industries, from the decline of plastic straws to the rise of solar panels on residential homes. The reality is that both individual and systemic actions are necessary. While one person switching to a reusable bag may not stop climate change, millions making conscious decisions can influence corporate policies and push for stronger climate legislation. It is not about one or the other, it is about how collective consumer pressure can drive larger systemic shifts. What governments and corporations need to do, policy changes that could accelerate reversal. While personal choices can contribute to a greener future, large-scale climate reversal requires policies that force industries to change. Governments have the power to regulate emissions, incentivize clean energy, and hold corporations accountable for pollution. Yet, many leaders hesitate to implement strong climate policies due to economic pressures and political lobbying. One of the most effective policies is ending fossil fuel subsidies. Currently, many governments continue to provide financial support to coal, oil, and gas industries, making it cheaper to pollute than to invest in clean alternatives. Redirecting these subsidies toward renewable energy projects could accelerate the transition to a low-carbon economy. Stronger carbon pricing regulations are also needed. Carbon taxes, emissions trading systems, and stricter pollution penalties can push companies to reduce their environmental impact. However, these policies must be enforced globally to prevent corporations from relocating operations to countries with weaker regulations. Investing in clean infrastructure is another critical step. Governments must prioritize public transportation, renewable energy grids, and energy-efficient buildings. Countries that have committed to green infrastructure, such as Denmark and Costa Rica, are already seeing economic benefits alongside reduced emissions. Corporations also have a responsibility to act. Many large companies have pledged to reach net zero emissions by mid-century, but some commitments lack transparency and real action. Regulations should require companies to disclose their carbon footprint and ensure that climate commitments are backed by measurable reductions rather than greenwashing tactics. If policymakers and business leaders implement aggressive climate policies, climate reversal becomes a real possibility. Without their action, even the most committed individual efforts will not be enough to counteract industrial-scale emissions. Innovative startups and green technology companies making an impact. While governments and large corporations often move slowly, startups and green technology companies are driving some of the most innovative climate solutions. These businesses are proving that reversing climate change is not just a challenge, it is also an economic opportunity. Startups focused on carbon capture technology are developing ways to remove carbon dioxide directly from the atmosphere. Companies like Climeworks and Carbon Engineering are pioneering direct air capture technology that could become a key tool in large-scale climate reversal. While these technologies are currently expensive, advancements could bring costs down, making them viable at a global level. The rise of alternative protein companies is also making an impact on emissions reduction. Companies such as Beyond Meat and Impossible Foods have created plant-based meat alternatives that require significantly fewer resources than traditional livestock farming. With cattle farming responsible for nearly 15% of global emissions, shifting consumer diets towards sustainable options could reduce deforestation and methane emissions. Another promising area is sustainable energy storage. While solar and wind energy are crucial for a clean energy transition, one of the biggest challenges has been storing energy efficiently for times when the sun is not shining or the wind is not blowing. Companies like Tesla and Form Energy are developing new battery technologies that could revolutionize energy storage, making renewables a more reliable replacement for fossil fuels. Green startups are proving that climate action is not just about regulations, it is also about innovation. With the right investments and policies supporting these industries, climate reversal could become a profitable and scalable reality. The real impact of lifestyle changes, meat consumption, energy use, travel habits. While systemic change is crucial, there is no denying that individual lifestyle changes can contribute to emissions reductions. One of the most impactful choices is reducing meat consumption. The livestock industry is responsible for massive methane emissions, deforestation, and water consumption. Studies show that if the world adopted a plant-based diet, global agricultural emissions could drop by 70% by 2050. Even small reductions in meat consumption can make a significant difference when scaled across billions of people. Energy use is another key factor. Simple changes like switching to LED lights, using energy-efficient appliances, and reducing unnecessary electricity consumption can lower household carbon footprints. The widespread adoption of solar panels on residential homes has already demonstrated how individual choices can collectively contribute to a larger transition toward clean energy. Travel habits also play a role. The aviation industry alone accounts for 2.5% of global emissions, and with air travel expected to increase in the coming decades, emissions from flights could rise significantly. Choosing train travel over short-haul flights, carpooling, or using electric vehicles can help reduce transportation-related emissions. Governments can encourage these shifts by investing in high-speed rail networks and electric vehicle incentives. Waste reduction is another area where individuals can have an impact. Every year, over 300 million tons of plastic are produced, with much of it ending up in landfills and oceans. Simple actions like reducing single-use plastics, composting food waste, and recycling responsibly can help lower overall environmental impact. While individual actions alone will not reverse climate change, they set the stage for larger cultural shifts. When millions of people demand sustainable products, companies are forced to adapt. When people vote for leaders who prioritize climate policies, governments take action. Personal choices influence the marketplace and policy decisions in ways that, when combined with systemic change, can create a powerful force for climate reversal. The challenge ahead is massive, but it is not impossible. A combination of government action, corporate responsibility, technological innovation, and individual lifestyle changes is needed to create a sustainable future. The question is whether we will act quickly enough to prevent the worst effects of climate change, or if we will continue delaying until the damage becomes irreversible. The next step is understanding what the future holds. If we succeed, how long will it take to see real change? And if we fail, what kind of world will we be leaving behind? The future: what happens if we fail or succeed? What happens if we don't reverse climate change? Worst case scenario: if efforts to reverse climate change fail, the consequences will unfold in increasingly devastating ways. Scientists have warned that global temperatures could rise by as much as 3 to 5 degrees Celsius by the end of the century if emissions continue unchecked. This level of warming would fundamentally alter life on Earth, triggering irreversible damage to ecosystems, economies, and human civilization. Rising sea levels would accelerate, submerging low-lying cities such as Miami, Jakarta, and Venice, and forcing the relocation of hundreds of millions of people. Coastal regions worldwide would experience increased flooding, salinization of freshwater supplies, and loss of critical infrastructure. Small island nations, including the Maldives and Tuvalu, could disappear entirely beneath the ocean. Extreme weather events would become more frequent and severe. Heat waves, wildfires, hurricanes, and droughts would devastate agriculture, making food production increasingly unstable. Countries that rely on consistent seasonal weather for farming, such as India, Brazil, and the United States, would see major disruptions to crop yields, leading to food shortages and higher prices. Biodiversity loss would accelerate, with mass extinctions occurring as ecosystems collapse. Coral reefs, which support 25% of marine life, would vanish due to ocean acidification and rising sea temperatures. The Amazon rainforest, often referred to as the planet's lungs, could transition into a savanna-like state, releasing vast amounts of stored carbon into the atmosphere and worsening global warming. Human health would be directly impacted, with higher temperatures leading to the spread of vector-borne diseases such as malaria and dengue fever. Air pollution would worsen respiratory illnesses, while heat stress would cause fatalities in vulnerable populations. Water scarcity could lead to geopolitical tensions, with nations fighting over dwindling freshwater resources. Economic systems would struggle to cope with the financial burden of constant climate disasters. Insurance markets would collapse in regions prone to wildfires, hurricanes, and floods. Governments would face rising costs for disaster relief, infrastructure repair, and climate adaptation. A global economic downturn could result as supply chains are disrupted and industries dependent on stable environmental conditions, such as agriculture, fisheries, and tourism, face massive losses. The most alarming possibility is that climate change could trigger self-reinforcing feedback loops, making the warming process uncontrollable. The release of methane from permafrost, the collapse of major ice sheets, and disruptions in ocean currents could push the climate into a permanently unstable state, making human intervention ineffective. The longer action is delayed, the harder it will be to undo the damage. If we succeed, how long would it take? A realistic timeline for climate reversal. Reversing climate change is not an overnight process. Even with immediate and aggressive action, it would take decades to see significant improvements. The first step is achieving net zero emissions, meaning that the amount of greenhouse gases emitted is balanced by the amount removed. If global policies align with scientific recommendations, net zero emissions could be reached by 2050, as outlined in the Paris Agreement. Once emissions are stabilized, the process of reducing atmospheric carbon would begin. Natural methods like reforestation and regenerative agriculture could start absorbing excess CO within a few years, but full ecosystem recovery would take several decades. Carbon capture technologies, if deployed at scale, could accelerate this process, but the challenge lies in making them efficient and cost-effective. Scientists estimate that to restore carbon dioxide levels to pre-industrial levels, large-scale carbon removal would need to continue for 50 to 100 years. The Earth's climate system takes time to respond to changes. Even if emissions stopped completely today, temperatures would continue to rise for several decades due to the heat already trapped in the atmosphere. Ocean acidification, glacier melt, and extreme weather patterns would persist before gradually stabilizing. If all available solutions, renewable energy, carbon capture, ecosystem restoration, and policy changes, are aggressively implemented, meaningful climate recovery could be seen by 2100. While this seems like a long timeline, every fraction of a degree of temperature reduction matters. Preventing catastrophic climate shifts now will determine the conditions for future generations. What future technology could change everything? Nuclear fusion, and new discoveries. While current solutions focus on existing renewable energy and carbon removal technologies, future breakthroughs could dramatically accelerate climate reversal. One of the most promising developments is nuclear fusion, which has the potential to provide unlimited, clean energy without the radioactive waste associated with traditional nuclear power. Unlike fossil fuels, fusion generates energy by fusing atomic nuclei together, mimicking the process that powers the sun. Scientists at institutions like ITER and MIT's Plasma Science and Fusion Center are working on making fusion commercially viable within the next few decades. If successful, fusion energy could eliminate the need for coal, oil, and natural gas altogether. Artificial intelligence is also playing a growing role in climate solutions. AI-driven models are improving weather forecasting, optimizing energy grids, and enhancing carbon capture efficiency. Machine learning algorithms can analyze vast amounts of climate data to predict environmental changes and guide more effective mitigation strategies. AI is also being used to monitor deforestation, track ocean temperatures, and detect methane leaks from industrial sites, helping to enforce climate policies and hold polluters accountable. Another emerging technology is synthetic biology, which aims to engineer plants and microbes to absorb carbon dioxide at unprecedented rates. Researchers are exploring ways to genetically modify plants to have deeper root systems that store more carbon in soil or to create microorganisms that break down plastic waste. These bioengineering solutions could revolutionize carbon sequestration efforts and help reduce pollution. Advanced geoengineering techniques are also being considered, such as space-based reflectors that could reduce solar radiation reaching Earth or chemical processes that remove methane from the atmosphere. While these ideas are still theoretical, they represent the kind of innovation that could become necessary if traditional methods prove insufficient. Controversial insight: could we create an artificial climate-controlled planet? As the urgency to address climate change grows, some scientists and futurists are exploring the idea of creating an artificially controlled climate system. This concept involves using advanced technology to regulate global temperatures, manage weather patterns, and stabilize atmospheric conditions. One possibility is large-scale stratospheric aerosol injection, where fine particles are released into the upper atmosphere to reflect sunlight and cool the planet. This would mimic the effects of volcanic eruptions, which have historically caused temporary cooling periods. While this approach could provide immediate relief from rising temperatures, the long-term effects remain uncertain. Sudden termination of such programs could result in rapid warming, leading to extreme climate shocks. Another concept is geoengineering megastructures, such as massive space mirrors or artificial cloud layers that could block excess solar radiation. These ideas are still in the realm of science fiction, but as climate conditions worsen, extreme solutions may gain more attention. Critics argue that relying on artificial interventions instead of reducing emissions could create dangerous dependencies, leading to unintended consequences. The ethical implications of a controlled climate system are also concerning. Who would be responsible for managing the global climate? Could such a system be manipulated for political or economic gain? Would some regions benefit at the expense of others? The risks of centralized climate control could outweigh the benefits if not managed carefully. Despite the controversies, some experts believe that advanced climate engineering could become necessary if traditional efforts to reverse climate change fail. While reducing emissions, restoring ecosystems, and investing in clean energy remain the top priorities, future technologies could serve as a last resort to prevent planetary collapse. The future of climate change will be determined by the choices made today. If humanity takes immediate and coordinated action, the worst outcomes can be avoided. If efforts remain slow and divided, future generations may inherit a world with extreme weather, food scarcity, and geopolitical conflicts driven by climate instability. The final question remains: what will it take for people, governments, and